All right, peeps, it's Jamie and I'm back for another forecasting video. We just finished our moving average 5 forecast. We've got our forecast. We've got our mean at forecast error, our mean absolute error, our mean absolute percentage error, our mean squared error. For now, we've got that for MA5 and MA3. And here we are ready to tackle our next one, which is exponential smoothing. So I have my exponential smoothing tab. And like I did when I started my MA5 forecast, I'm going to copy my section of errors from, I'm going for my MA3 forecast, but you can pick from wherever you want. I'm going to copy it, I'm going to line it up, and I'm going to paste it. This time, rather than having MA3 or MA5, we are going to create an exponential smoothing forecast. And I'm just going to place ES there. Similarly, we aren't going to have the same kind of color palette. So I've got 3 rows, 5 columns. I'm going to steal my formatting. Oops, that was not necessary. And I'm going to start off by making an exponential smoothing forecast. Well, I guess maybe that's not how I'm going to start off. I got ahead of myself. I am going to clear out my previous forecasts. I'm going to double check by looking at my errors to make sure that they're referencing the right cells. My tells for that are that the forecast error at this stage, once the forecast is missing, should equal exactly the previous or that year's level of attendance. Our absolute percentage error should be 100, and this squared forecast error will be pretty large. It's okay if it doesn't show all the way up. So in making an exponential smoothing forecast, before I get started, I have to decide what preliminary level of alpha I want to use. And alpha is that smoothing constant. And by selecting alpha, we essentially say how much relative weight we want to give to the most recent actual observation versus how much we want to give to a weighted average of all the previous observations. And I'm choosing 0.2 to start with. It's arbitrary because once we get our exponential smoothing forecasted complete and our errors tidied up and calculated, we will use Solver to determine the level of alpha that minimizes our errors. So to make that exponential smoothing forecast, the formula is going to rely on knowing the previous year's actual attendance and the previous year's forecast. Well, so obviously we can't do anything here because we have neither attendance nor forecast previous. And in the second year, we've got attendance, but we don't have forecast. So I'm going to just start by assuming I was right on in my first year. So I'll let my forecast look like my actual value, but only for that first year. Because of that, I don't want to calculate a forecast error because it would be fake, right? It would be 0 and it would underestimate the errors of this forecast. Okay, ready to get started? So the exponential smoothing forecast uses this formula. A forecast for exponential smoothing says that our forecast is going to be equal to our alpha, make it sticky, multiplied by the previous attendance. So 20% from previous attendance, and the 80% is going to be from the previous forecast. So we're going to add to that 1 minus alpha. There's that 80%. Command T. Close the parentheses, multiply it by the previous forecast. In this case, we're going to end up, obviously, with 20% of 858,000, 80% of 858,000. We end up with 858,000. That's fine. But as we drag this down, we'll see that that forecast changes. And the larger the value of alpha, let's go up to 0.5 here, the closer each forecast comes to resemble the previous actual level of attendance, and the less it looks like the previous forecasts. Because now I'm saying, well, I'm going to forecast next period as 90% of this period plus 10% of the previous forecast. And because the previous forecast is always a function of previous attendance, it basically just makes this a weighted average of the previous values of our time series. All right, before I take a look at errors, I'm going to pop this back to 0.2. That way, we'll all sort of be in the same place. If I scroll down to the bottom and I calculate, well, here I've got my forecast, right? Oops, no. Aha, so click in that. We need to make sure that that is also equal to the exponential smoothing forecast. So I'm just going to drag it down and then deal with the formatting later rather than re-entering the formula. So I've got my forecast, which is equal to my alpha times my previous level attendance plus 1 minus alpha times my previous forecast. Then my mean forecast error, wow, look at that, that's quite high, 9,000. We were looking in the 600 to 800s before, but I'm going to double click on it because I need to double check that I'm getting forecast errors everywhere that I need. And look, I don't. I don't want a forecast error here because we know that that's not a real forecast, but I will take it for the previous 2 years. I'm going to count this as a real forecast. And I'm going to use that forecast error, the absolute error, the percentage error, and the squared forecast error. Okay, now let's go back down and double check our averages to make sure that they reference all the forecast errors that I have. So if you're looking at the book and you're looking at the formula for these forecast errors, for the mean forecast error, the mean absolute forecast error, you'll see it's got kind of a complicated formula. And that's because it's trying to be specific about how many forecast errors you should have, and it's trying to give you an actual exact number. And the way I like to think of it is great. You know, it might be from time equals k or n minus k up to n, right? But we just want to tell ourselves or remind ourselves that we only want to average errors for periods where we have a forecast, and we want to make sure that we average all of them. So really it's just the average of the forecast error, and then as we move across, we're looking for the average absolute error, the average percentage error, the average of the squared error. And now we've got some numbers. So our exponential smoothing average, or forecast, initially appears to do much, much worse than either the moving average 5 forecast. We can see that because the forecast error is larger, showing more bias, and then the absolute error, the percentage error, and the mean squared error, right? Do you see that? They are all larger. Same thing if we compare it to moving average 3. The exponential smoothing forecast is worse in all regards. However, when it comes to exponential smoothing, we don't need to be discouraged. If we think of moving average forecasts, do we want to average 3 periods or do we want to average 5 periods? You know, that's fine, but there's a limited number of periods we want to try because we've got to duplicate this analysis for each iteration of moving averages that we'd want to attempt. Exponential smoothing has an advantage. One is that, or actually the advantage is that this whole forecast, every forecast is linked to this particular cell. If we change the value of alpha, everything in our table changes. And we know that the best forecast, at least we're going to assume that the best forecast for the future is the one that's done the best job on the past data, right? The one that's best able to reproduce the data we already know. So exponential smoothing can change as we change the value of alpha. Wouldn't it be nice if we could just figure out what alpha led us to have the lowest, let's say, absolute percentage error? Well, we can do that. And we do that using a function called solver. Solver can be found in the Data tab over to the right. You might have to pause and download it. It's an Excel add-in. However, you got Data Analysis Tool Pack for your computer is how you're going to get Solver. Google it if you need some help. But once you got it, we're going to open it. Let's see. So when we open our screen, when we open Solver, we get a box that says Solver Parameters. All right, and it has some options. There's a set objective, or it might say set cell, something like that. And that's the thing that we want to, it's our outcome. And in this case, we want the best forecast, and our objective is getting the best forecast. And we're going to measure it by our mean absolute percentage error. So my objective cell is going to be the cell that has my mean absolute percentage error in it. And then I can set that cell, I can maximize it, I can minimize it, I can try to set it to a specific value, and I'm going to minimize it. And then by changing the cell, I want to change alpha. Nope. My objective cell is my absolute percentage, and my variable that I want to change is alpha. Okay, great. There are some rules around alpha. One is that alpha has to be greater than or equal to 0, and it has to be less than or equal to 1. It's got to be a value between 0 and 1 inclusive, because we're sort of thinking about it as a percent. What percent of our forecast do we want to come from previous levels of attendance, and what percent do we want to come from the weighted average of all the previous values of attendance? So current versus more historic. So Solver will give us some constraints. It'll allow us to say that alpha needs to be between 1 and 0 inclusive, but we have to enter it in two pieces. So we're going to add a constraint. And the cell reference here is that alpha, it gives us a lesser than or equal to. It has to be less than or equal to 1. Now I'm going to add another one for it needing to be greater than or equal to 0. So I'm going to hit add, and this box will just sort of stay here. And the same thing is going to be that I want alpha to be, from that drop-down menu, I'm going to select greater than or equal to 0. And this is an example of an optimization problem. I want to find the optimal level of alpha to minimize my absolute percentage error. Down here and under select a solving method, choose GRG nonlinear, and then hit solve. So it says it's found a solution. Let's see what happens. I'm going to click OK. And on my data, for this data set on Badlands from 1979 to 2023, I've got one place where my error was equal to 0. When my forecast hit the actual mark, I had to eyeball that real quick. But the optimal level of alpha to minimize my absolute percentage error is 0.514. I'm going to steal some formatting here, because everything's better with formatting. Add some decimals. That's the optimal level of alpha for this data set. Yours will be different. But what you should see is that your mean absolute percentage error is smaller than it was before. So now, if we want to do some comparisons, play the comparison game here with exponential smoothing, I'm just going to focus on our mean percentage error for a second. 7.72% on exponential smoothing, 8.73 on MA5, 7.56 on MA3. So MA3 is still looking like the best option given my data. Yours will probably be different, and that's okay, because that's what we're trying to do, is given the nuances of each individual data set, find the forecasting method that was best able to explain what was seen in the past. Then we'll say, sure, that might be the best bet for envisioning the future. I'm going to steal some formatting. 1, 2, 3, 4, 5. Place it here. Redo my percentages. Double check. All right, and I'm feeling pretty happy with this. Okay, so this, my friends, is my exponential smoothing forecast. Your numbers, of course, will be different, but the idea is the same. And with this, the exponential smoothing forecast thinks that we're going to have 1,047,326 visitors next year. It has a mean forecast error of 8,366, which tells us that it underestimates more than it overestimates. That means that we've got a bias in the underestimation direction. The mean absolute squared error is 83,184, which means that that's the number, the distance we are away from the actual value or the actual attendance each year on average, and that works out to being about 7.72% of our actual level of attendance. All right, happy forecasting, and I will talk to you soon.